Hello, Lily J, and anyone else who happens to catch this. I'm Bill Wyzant, and I'm going to talk about the thin lens formula and how you solve for the object distance O here in this diagram. Let's look at the problem the way it was set up. The actual light sensor, the size of a digital camera, is 14.9 millimeters by 22.3 millimeters. Now, that's some interesting information, but it's not necessarily part of the problem in and of itself. You want to take a photograph of your friend who is 2 meters tall. That's certainly needed in the problem. Your camera has a 50 millimeter focal length. How far from the camera should your friend stand in order to produce a 22-meter tall image on the light sensor? Lily did the right thing in knowing that she needed to do the 1 over the thin lens formula. And so this is correct. 1 over the focal length is correct. 1 over the image distance is correct. Whoops, this is not the image distance. This is the height of the image. The height of the image and the image distance are along different axes. So let's go figure out how we deal with that little problem. Here I set up a diagram because this simplifies our thought process on this. The height in the camera of the image and the height of our object, the tall boy, are vertical. I is the horizontal distance between the lens and the image screen, and sigma is the horizontal image object distance, I should say horizontal object distance, O. We're using the lens formula, and we're using the relationship I over H, which is the triangle on the left side, equals sigma over the height of the boy on the right side, which are both big numbers, but the ratios are the same. So I is equal to O times small h, meaning the image height, divided by the height of the boy. If we look here, we can see that we can rearrange this, substitute in for I, and put the O up here on the top. And if we multiply the left term by H over H, we end up with a common denominator, OH. H plus H over OH. If we flip that around, we can say OH over H plus H is equal to the focal length. But the focal length isn't what we're trying to get. We want to then multiply both sides by the known terms on the right side so that we end up with H plus H, the height of the image plus the height of the boy, divided by the height of the image, times the focal length equal to the object distance, the distance the boy needs to stand from the camera. This distance is equal to F times HO plus H over H, meaning the height of the boy plus the height of the image over the height of the image. Now this is almost H and I are almost the same, but not quite. This means that we end up with multiplying this out. 4,595 millimeters. And we can easily turn that into meters. Oops. To 1 decimal place. Having trouble with my screen here. Okay. To 1 decimal place, we have 4.6 meters. And that's the answer to 1 decimal place. We can check that answer. We'll call this check. By plugging the numbers that we know into the relationship between the two triangles up above. I is equal to h, the image height over the boy's height times the focal distance. And we calculate for I, and I turns out to be, if we put it in millimeters, 50 millimeters, 50.55 millimeters. Note that 50 millimeters is the focal length of the lens. The lens adjusts that distance to the image plane by moving forward just a bit so that it's slightly longer on its image length than the focal length in the camera. And that's it. Just remember, the best thing to do is to draw an image in the beginning and then look at the relationships between the things that we know, that's these things, and the things that we don't know. Thank you.